everyone. So in this video we will talk about traveling waves. We'll cover the topics of wave motion and then waves on a string and then three-dimensional waves where we will talk about decibels, a unit of intensity, etc. So let's start talking about wave motion. So what is wave motion? We can just for an example, let's see this quick short video. So I have a plot of a function that looks like f of x minus vt, where x is the position, v is the velocity, and t is time. And I'm plotting that function as a function of x at some time t. So this initially the time t is 0 seconds. So if I plot this function, let's say that the function looks like this this plot. Can you recognize this graph? That's actually a sine curve, right? So I start that sine curve off at time t equals 0. When time t equals 0, that v times t term is also 0. So I'm really plotting f of x as a function of x. All right. So what happens if I add that negative v times t and let the time evolve? You see that as time goes forward, this plot just moves in the positive x direction, right? Now it turns out that this is true for any wave that is of the form f of x minus v times t. So any function that looks like f of x minus v times t moves in the positive x direction as time t progresses. So if t increases, f of x minus v times t will move in the positive x direction. And similarly, if I have a function that looks like f of x plus v times t, that's going to be moving in the negative x direction. So let's see an example of that. So this is an example of a function that looks like fx plus vt. So unlike the previous plot, this function is no longer sinusoidal. This is a different function. I've just specifically picked a different function so that I can convince you that as long as the function looks like f of x plus vt, it's still going to be moving to the left. So if I now play this video, as time goes on, you will see that this function, the peak in this function, is moving to the left. So that's the property of the function, and it comes from the fact that this is a function of x plus vt. Okay, so in order to discuss this in a little more detail, we'll look at the functions themselves. So this function, f of x minus vt, has that form, meaning at time t equals 0, it was this blue curve, and at time t equals 1 second, so a little bit later, it's this orange dashed curve. So it progressed, and it moved to the left, so to the right. So this is a right moving wave. And similarly, at time t equals 0, this function f of x plus vt now was this blue curve, and time t equals 1 second, that's the orange curve. Clearly this moved to the left. So x plus vt, this function is a left moving wave. Great. So some interesting things that we should remember. There's something called a phase of a wave, and the phase of a wave is just equal to kx plus omega times t. So that's the phase of a wave, where this k is a new idea. It's called a wave number, often wave number. And omega, we are familiar with omega. Omega is just the angular frequency of the wave. Phi is the phase. Okay, now it turns out that this function phi can be rewritten to take either the form x minus vt or x plus vt. And so I said that the phase is kx plus omega t, but it can also be kx minus omega t. Both options are possible. So we can rewrite phi as k times x plus or minus vt. So now you see that the phase itself looks like this is some function of x plus or minus vt. Okay, and how is the function obtained? Well, you take x plus or minus vt and multiply it by k. All right, so if we we distribute the k across the two terms inside the brackets, then we get kx plus or minus kvt, and that's equal to phi. So clearly k times v must be equal to the angular frequency omega, right? Look, the first term looks just like kx, so the second term must look like omega times t. So k times v turns out to be omega. So this is a relationship that we found. K is the wave number. Wave number equals k. And for periodic waves, so one example of a periodic wave is this. So this is a periodic wave. Periodic wave. Periodic because it repeats itself after some period. Okay, so because it repeats itself after a period, it's called periodic. And for a periodic wave, this distance from here to here, that's called the wavelength lambda. So that's the wavelength. Okay, now if this is a sine curve, so it probably would have repeated one more time, and I didn't draw the repetition. One can also say that this length, the length from one peak to the next peak, right, that length is also the same as lambda. The wave number turns out that it is related to lambda. Wave number k is equal to 2 pi divided by lambda. Now earlier I said that this v is a speed or a velocity, right? The v over here, the v over here, that v. It is a velocity, but what does it physically represent? Well, clearly in these pictures, it's representing how fast the wave function, the waveform itself is moving to the right or to the left. So this v is often referred to as the phase velocity of the wave. V is the phase velocity. The phase velocity v can be found in terms of the angular frequency omega using this formula here, right? So the phase velocity v is equal to omega over k. Remember, k is not the spring constant anymore. K is not spring constant, right? K is, what is k? K is the wave number. It's a different quantity. It's equal to 2 pi over lambda. It might not, it doesn't have the same units as spring constant. So don't confuse that. V equals omega over k, and if I put in k equals 2 pi over lambda, then I get from that V equals omega over k, which is 2 pi over lambda. So this velocity equals omega times lambda over 2 pi. Okay. In addition to this, you can also see that omega over 2 pi. What is omega over 2 pi? Omega over 2 pi is just the frequency, right? Omega over 2 pi is the frequency of the wave. So we can just write this as f times lambda. So phase velocity of a wave is equal to its frequency times its wavelength. Phase velocity equals frequency times wavelength. So in a lot of problems you may encounter a couple of these, and you may need to find the third one. So for instance, if you know the frequency and the wavelength, you should be able to find the phase velocity. If you know the frequency and the phase velocity, you should be able to find lambda, the wavelength, etc. Right? This is an important formula, so I'm going to start this over here. We're going to use this later on in our course.